Kyle. Be on high alert. There's a pie thief among us. Trust no one, and protect your pie above all else.
Hi, I'm Kyle, and today I'm going to show you how to keep your pie safe using a pie. Next, we'll cover the parts required for this project. We are using the Raspberry Pi 3 Model A+, and a Hall effect sensor which can detect magnetism. So then we'll use a magnet to trigger that, and from there the GPIO will activate on the Raspberry Pi, which will then activate this solid state relay to send voltage to our solenoid, which will retract when a magnet is present. I made this custom GPIO breakout board for the Raspberry Pi. Just mounts on the male header there. It's nice because it retains the male headers. I also added screw terminal blocks which allow you to connect your wires in a more permanent fashion. In addition to these parts, we'll be using a screwdriver kit from SparkFun, some jumper wires for the perf board, and some wire. Most importantly, we'll need a case to protect your Pi. Now that we have our parts, let's begin assembly. I designed this board and sent it off to Osh Park, and then I brought it to the lab for assembly. It starts off with this female header with long pins that will act as male headers on the top side, so we retain the male headers that were originally on the Raspberry Pi. Then it breaks out those same pins to these screw terminal blocks that allow you to connect wires semi-permanently. Next, I'll be soldering up the solid state relay board, and that uses the SparkFun perf board. And this differs from a traditional perf board because 3 pins are connected together. So these 3 pins are connected, these 3, and these 3. So they're all connected vertically. So you need to be aware of that before we start soldering, or we'll have to start cutting those traces. So as you can see on the top of this, there's no copper, so the components need to go on this side so we can solder on the back. We'll start with this connector from the solenoid. So we have the solenoid connector up here, which we'll just plug in like that. We have a wire terminal block here, so we're going to have positive 12 volts to drive the solenoid, signal from the Raspberry Pi, and ground from the power supply. The signal will come in on the center wire, go through this resistor and go to pin 1 of the solid state relay. Ground will go to pin 2 of the solid state relay. So there's actually like a little LED inside here that activates the output. Then we have the 12 volt positive coming up to one of the switch sides of the relay, and the other side will output positive to the solenoid when the LED is activated inside. And then we'll have a ground connect to the solenoid from this purple wire here. We'll be connecting 3 wires to the Hall effect sensor. We will have a ground, 3.3 volt, and a logic output. The reason we're using 3.3 volts is because the logic input of the Raspberry Pi is 3.3 and cannot accept a higher voltage value. So to solder these, I find it easier to tin the wire first before I solder it, so I don't have to add solder while I'm connecting it to the lead of the device. I'll just add a little bit of solder to the wire, and then it'll stay there. And then I'll bring the wire in and next to the lead there, heat it up, and that's attached. Because the leads of the sensor are uninsulated, we're going to want to add some heat shrink to insulate each lead from the other ones. Measured out just a little bit longer than the leads, so we cover the wire insulation. To protect the sensor a little more and add some strain relief, we'll add another piece of heat shrink that's a little bit larger to go around these 3 pieces. So now that we have this complete, I like to twist the wires together with a drill so it makes them for a nice clean installation. So to twist the wires, it's pretty simple. All you need to do is have a vise or somebody hold the one end of the wires, and then you take the other end and insert them into your drill chuck, and twist. Now that we have everything soldered, let's put the components in the case. I designed this 3D print to mount the solenoid in the case. I'm going to attach this with epoxy, so I'll mix that up right here. Now that our epoxy is set, I'm going to use hook and loop fasteners to put the rest of the components in the case in case I need to ever replace them. Next up, we'll connect our cord to our power supply. We have our brown line wire, our blue neutral wire, and our green and yellow ground wire. Next up, we'll connect the 5-volt power lines from the power supply to the Raspberry Pi. So when testing this, I found that if I used a USB cord to power the Pi, I had a significant voltage drop and the Pi wasn't getting enough power, especially if I was running NeoPixels from one of the GPIO. Now that we have the wires from the power supply routed to the Raspberry Pi, let's do a test power up. And we have the red light on our Raspberry Pi here and a green light on our power supply, so we're good to go. Next up, we'll mount the solid state relay board. Then we'll run the power, ground, and signal wires to the solid state relay board. I'm going to use blue for 12 volts, yellow for signal, and black for the ground. Next up, we'll put the solenoid in place. So in our 3D print, I added these elongated slots so I can adjust the distance of the solenoid from the actuation point. Next up, we're going to find a mounting place for our Hall effect sensor. My first thought was to mount the Hall effect sensor here, but I think that's a little too obvious. We're going to go with a more conspicuous area over here. Because this case has these rectangular recesses, I'm going to mount the Hall effect sensor into those so it's closer to the surface for the magnet to activate it. So as I said earlier, the Raspberry Pi GPIO is at a 3.3 volt level. So we're going to run 3.3 volts into this Hall effect sensor, and then the signal coming out will be 3.3 volts as well. So last step for assembly, we'll need to cut a hole in here that the latch will engage with. So in order to get the placement correct, I closed it up like this and made a scribe mark on each side of the latch. So then I have the position centered correctly. Now that we have this all put together, let's go program the Raspberry Pi.
To begin the code, we're going to need to boot up our Raspberry Pi into Raspbian. That requires that you install Raspbian. There's lots of instructions online on how to do that. So once we have your Raspberry Pi desktop up and running, we'll go ahead and click the Start button in the top left, go into the Python IDE, and then we'll start coding. First thing we're going to want to do is save the file onto your desktop so that in the future it's easier to save it and so we don't lose anything. From that point, I added a comment at the beginning of the code to kind of explain the project and all of the connections and all that information. Once I have the comments in, I begin importing libraries. First library is going to be the board library, and then we're going to need to import the NeoPixel library if you're going to use NeoPixels. So in order to import that, we first have to install it. To install it, we have to open up the terminal, and then we have to type in this line of code. The line starts out with sudo pip3 install, and then the rest of the information for the NeoPixel library. Once that's finished installing, we'll go ahead and go back to the code, and then we'll finish adding our libraries that we'll need. So we'll need the rpi.gpio, and that's going to allow us to control the GPIO pins. And then we're also going to import the time library that will allow us to use sleeps and delays in the code. From there, we'll establish our pixels. So we do pixels equals neopixel.neopixel parentheses board.d18, which is our pin that we'll be driving the NeoPixels with, comma 50. And 50 is the number of pixels on your strip. Modify as you need. Next line is gpio.setWarnings false. That will just disable any warnings that come up saying that your GPIO is already in use with something else. Next up, we'll do the GPIO setup. We'll set up pin 21 as a GPIO out, and then we'll do the initial equals GPIO low, so that just sets it low at the beginning, and then from there we can change it. And then we'll do a GPIO.setup pin 17 as a GPIO in, That's going to allow us to read the input from the Hall effect sensor. Then we'll establish a lights on variable, and that will control the state of the lights. So 0 will be lights off, 1 will be lights on. Then a while 1 loop. While 1 allows anything in the code there to run forever after the while 1. From there, we'll do a print GPIO input 17, so that allows us to read the status of pin 17 in the shell. So it will read out line by line the value of GPIO 17, as long as there's no magnet next to the Hall effect sensor. If there is a magnet next to it, it will display 0. Then we'll do a half-second sleep. Then we'll begin a while GPIO input 17 equals 0. So that's while a magnet is close to the sensor. We will then do a GPIO output 21, 1. So that activates the solid state relay to then conduct 12 volts to the solenoid, thus retracting the solenoid, allowing us to open up the case. Next, we'll do lights on equals not lights on. So that will toggle the lights on variable every time we enter this while loop here if the Hall effect sensor is active. So every time you bring the magnet up, it'll turn the lights on. The next time you bring the magnet up, it'll turn them off, and it'll just toggle them on and off. So then we'll do a if lights on. We will then pixels.fill 255, 200, 0. So that's like a golden yellow treasure chest look. Then an else statement. So if the lights on variable is equal to 0, we will turn the pixels off. We'll do a pixels.fill 000, so that's turning all of them off. Then we'll do a 1.5 second sleep to leave the latch retracted for 1.5 seconds. You can modify this if you'd like to leave it longer. And then we will print the status of the GPIO 17 pin again. And finally, do a GPIO.output pin 21, 0. So that will bring that 21 pin low again, deactivating the solid state relay, deactivating the solenoid, and thus latching the briefcase. Final thing that we'll need to do is go into our terminal again and edit our rc.local file. That will allow us to run this script on boot every time the Raspberry Pi is turned on. It'll just automatically be running, so we don't have to do anything with that. So the code to get into the rc.local file is sudo nano /etc/rc.local. That will allow us to edit the file, and what we're going to do is right before the exit 0 at the end of the file, we will add a line that says sudo python3 and then our file location, and then at the end of that line we'll put an ampersand. So that allows this script to be forked, so it's not the only thing running. It will be able to be multi-threaded, so that just allows the Pi to boot. Because this is a while loop, it will enter this code and continually run. That won't allow the Pi to finish booting if we don't ampersand or fork that script. With all that done, we're ready to test.
Now that we finished our Python program and we modified our rc.local file to make the program run on boot, let's give it a try. As you can see, after I finished programming, I thought it would be cool to add some NeoPixels to the project. Now that we know everything works, I need to go see a man about a Pi.
Like this video? Want to learn more about other interesting projects from Digikey? Subscribe to our channel.